Symmetries and angular momentum. Previously, we introduced the stationary states of hydrogen atom with 3 quantum numbers. Principal quantum number n, angular momentum quantum number L, g-directional angular momentum quantum number m. And here, energy, momentum, angular momentum are fundamental conserved quantities. And these are actually related with symmetry. We know momentum, energy should be conserved. And we know there is a parity, and it also should be conserved. Momentum is related with translation space. Energy is related with translation in time. And parity is related with the symmetry of potential shape. If the potential shape is symmetric under reflection, for example, we previously introduced the symmetric potential, where potential is symmetric this way. So region 1, 2, and 3, and then in region 2 potential is 0 from minus A to plus A, and the region 1, region 3, they have the symmetry potential. We can see they have mirror like reflection between this side and this side. Then we have parity. Likewise, there is also angular momentum, which should be conserved, and this is related with rotational invariance. If you rotate your laboratory and everything that affects your experiment through some angle, the results of your experiment should not be affected. And this class is mostly related with angular momentum. Rotational symmetry and angular momentum. Angular momentum of a particle is defined like this: L equal to R cross P, and based on that we have this. So you go through cross product, then this is obtained, and based on that the quantum mechanical representation is shown here. You will see if you go through this calculation, Lx, x, then it is 0, because basically there is no x correlated component. It is either y or g directional, mathematical operators we have. So Lx, x, because the commutation means, as you know, Lx x minus x Lx, okay. Lxy equal to IH bar G, Lg Lx comma Z, because the commutation, then we have minus IH bar Y. Then we summarize this, Li comma xj, so it's like x1 is x, x2 y, x3 is g. Okay, and also this epsilon ijk is Levi-Civita symbol. So it is like this. It is like 1, 2, 3. If it is rotated like this way, it's positive. The other way, negative. Otherwise, this case is 0. So if it's like 1, 2, 3, it is 1, 2, 3 positive. If it is the other way, like 1, 3, 2, then negative. Okay. You will see this kind of ideas many times in angular momentum discussions, especially for this guy. If we consider x, y, z, if it's rotate like this way, it's positive. The other way, negative. So for Lx, the component consists of y or g component, y first and then g next, y first, g next. Rotate this way, it is positive. G first, y next, then g first, y next, then it is negative. Then you have negative sign. That is applied to 3 different components. Anyway, you have learned this kind of representation in undergraduate class. Okay. Also, if you go through Lx, Ly under commutation, then you will have IH bar Lg. So Li, Lg equal to IH bar epsilon ijk, Lk. So one cannot simultaneously have definite values of Lx, Ly, and Lg. They are not compatible, we can say. It means there is uncertainty. It means you cannot decide Lx and Ly at the same time. There should be uncertainty. Now, on the other hand, if we consider Lx square, then Li, Lx square, their commutation is 0. Then one can have definite value of L square and Li at the same time. Then we can call it they are compatible. If you cannot follow the mathematical details, still it is okay, because actually this is the topic to be discussed only in the second semester of physics department students. But we didn't go through those basic introductions, mathematical calculations. So it is way too hard actually compared to those quantum mechanics class. Still, quantum mechanics itself is considered to be one of the most difficult classes. So my suggestion is, if you cannot understand anything here in this class, still it is okay, right? I just suggest that you understand the meaning of angular momentum. And eventually in the end, at the slide 10, you will learn the angular momentum and spin under coupled state. That is the important part, because it is often found in semiconductor devices. Even in new materials, you will always see such, it is actually called as coupling. So you will see spin orbit coupling. Or spin orbit interaction, spin orbit energy. Such concepts are found in research papers, many cases. That is important part. And in this case, spin quantum number is fixed to be 1/2. Then its g directional component could be Sg, either 1/2 or -1/2. And most of the semiconductors, conduction band or valence band, angular momentum L should be either 0 or 1. Okay? Then we need to have this coupled state. Angular momentum could be either 1 or 0, and spin is 1/2. Then how about their coupled state? That is very important. That's what we want to discuss in terms of application in the end, after slide 10. So before slide 10, we will consider lots of complicated mathematical formulations. If you cannot follow those in detail, still it is okay. And yeah, again, mathematically complicated discussions. Actually, I myself go through all the mathematical calculations from undergraduate class and master class. Even in PhD class, early days, I calculated all the detailed angular momentum related quantum numbers, their wave function shape, but I couldn't use those in research papers, except angular momentum spin coupled state. Okay, so even though we are describing this mathematics, still it is okay. You don't need to induce any of these equations. Just consider there is something called raising and lowering operator. This is raising operator L plus equal to Lx plus ILy. The meaning of this guy is it will raise quantum number. You will see later on. And L minus, it will lower the quantum number. It is the linear combination between Lx and Ly. Then if we go through commutation again, it is non-zero. So non-zero. What does it mean? There is uncertainty. You cannot determine this guy and this guy at the same time. Well, Lx itself could be represented in terms of L plus and L minus. Okay, as shown here. Physics department, you will go through all those calculations. But here, we don't have time, so it is okay. You just recognize L plus and L minus. And also those LG, L plus minus, those are actually important operators. Sometimes we use this for some theoretical calculation, theoretical research papers, but I'm pretty sure most of you won't go to such area of research, so we'll skip those parts. And Lx square is defined like this, so you can only use these mathematical formulations if you need. You don't need to induce those. And previously we know there is the wave function part for angular equation, and the solution was YLM. So if we take L square operator, then it will lead to L plus 1 h bar square. Okay, and then YLM. So these are operator, these are eigenvalue. If we take LG operator, then you will have mh bar. And also there is bracket representation. This is often named as Dirac notation, and it is called as cat. So YLM has the same meaning of this LM within cat. So if we take the LG operation onto this LM, then you will have LM and the quantum number mh bar. And also the raising operator and lowering operator works on this LM, but you will change this quantum number, g directional angular momentum quantum number, multiplied by certain value. So please note that L plus acting on this LM, then you will have L m plus 1. This is the result of L plus operation, and the L minus operation will reduce the quantum number m into m minus 1. Okay, there should be this one multiplied by this one, square root L plus 1 minus m plus or minus. So if you apply L plus, you will get this part. If you apply L minus, then you will get this part. Okay. Yeah, we don't have time to induce this, but we just use this some sort of table. We just take it and apply it into our specific case. So that's why L plus is named as raising operator. Raise m to m plus 1. L minus, lowering operator. Lower m to m minus 1. So they are named as ladder operator. Okay. So general angular momentum and spin. So previously we considered angular momentum and its g-directional angular momentum, but now we can generalize those concepts. Now consider more general angular momentum J, which also include the concept of spin. Not only L equals 0, 1, 2, the integer number value, but there could be also half integer values. Because if you consider some generalized raising and lowering operator for J, then J plus minus. You just consider L plus minus for now, but let's say it is somehow generalized. Then let's say angular momentum quantum number and its g-directional component. You apply the raising operator, then you will change it into m plus 1. Okay, and this m starts from minus j to plus j. And if we all apply j minus onto this one, the maximum m value, it is j, so jj by many times, all the way down to j minus j. Then let's say we apply by n times, so we apply j minus by n times onto jj state. Then you will get the j, so each time you lower down this guy, so j minus n. So j minus n can reach only up to minus j. Minus j is the minimum value. So j minus n equal to minus j. Then you move this guy into here, minus n goes to right hand side, then n equal to 2j. Okay, here n, how many times we apply? So it should be 0, 1, 2, 3, and so on, right? So in this case, j should be n divided by 2. So J could be either 0, 1, 2 integers, or it could be half integers. 1 half, 3 half. So there could be some half integer values. Those are called as spin. So only from pure mathematical operation we found there could be half integer values, and these are named as spin. So not only the angular momentum, but also there could be spin state. And then combination of angular momentum. Consider two angular momentum operator J1 and J2. If we have two particles, for example, then first particle has the angular momentum related with J1, second particle is related with J2. And consider total angular momentum in terms of J1, J2 eigenstate. If they are under certain interaction, for example, let's say this guy could be electron, second particle could be electron or hole, positive charge. There could be Coulomb attraction or repulsion. They are coupled. Then we need to just simply describe J1 independently because they are coupled. And the other example is, let's say there's only electron. Electron got the angular momentum, and also there's spin. Classically, spin can be described like this. The electron can be rotating around its own axis, and also this electron can be rotating around the origin 0. It is separated by like r. It could be orbiting like this, it could be spinning like this, right? So there is two different kinds of rotation, and they are actually coupled. It will be explained later on in intuitive picture, but the basic idea is, if your spin is aligned like this, then you call it spin up, then electron should have half integer spin quantum number. Okay, it is projected along g-axis. Okay, it could be sometimes minus f. And this is when electron is rotating like this way. Electron could be rotating like the other way, around its own axis. Then if the electron is rotating like this way, we know there is current I. Okay, if the current is generated like this way with the orbital motion, then there should be magnetic field B. Okay, and this magnetic field will change the spin state. Okay, so angular momentum itself is always coupled with spin state in this way. So L and S, they are not independent, they are coupled. So let's say there is coupled electrons for angular momentum quantum numbers, like they should be same or sometimes different. Also, each electron itself can have angular momentum spin coupled state. So we need to consider the coupled state many times. That's what I'm talking here. J1 could be L, J2 could be spin. J1 could be L1, orbital angular momentum or angular momentum of one spinless particle, and J2 could be L2 of the orbital angular momentum of a second spinless particle. then now you need to consider their coupled state. Then you need to consider total angular momentum J. Okay. And the same rule for J is applicable like this way, just like we applied it to angular momentum. So J1 square applied onto J1 M1, you will have J1 plus 1 H bar square. Then J1G leads to M1H, J2G leads to M2H, J2 square. It is only acting on J2 M2, then you will have J2 plus 1 H bar square. If they are independent, if J1 and J2 are independent. Total angular momentum state. Then let's say coupled state somehow, then we use this kind of representation, J1 coupled with J2. Then we need to have J now. Then the same rule is applicable. Here, total angular momentum state is represented the original independent state J1, M1, J2, 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 M2. And this is the coupled state now. If it is independent J1, Jm equal to J1, M1, J2, M2. But if it is coupled, depending on coupling, you will have various coefficient in the middle. It is called as Clebsch-Gordan coefficient. And how can we get this Clebsch-Gordan coefficient for certain important cases of semiconductors? That we will discuss from next class. Okay, that's it for today.